Good morning, students. Welcome you all for next generation learning. Today we are going to see the subject physics, class 10, chapter number 13, magnetic effect of electric current. Topics: electric motor, electromagnetic induction. Under this electric motor, we are going to see what is meant by electric motor, application of electric motor, principle, construction, working, and conclusion. The first, electric motor. What is meant by electric motor? An electric motor is a rotating device. See here, it is a rotating device that converts electrical energy to mechanical energy. When we give electrical energy to electric motor, the electrical energy is converted to mechanical energy. So, the meaning of electric motor is an electric motor is a rotating device that converts electrical energy to mechanical energy. The application of electric motor. Electric motor is used as an important component in electric fan, refrigerators, mixers, washing machines, computers, MP3 players and etc. In car also the electric motor is used. So these are the application of electric motor. It is used in electric fan, refrigerators, mixers, washing machines, computers and MP3 players. So what is the principle of electric motor? The working principle of electric motor is based on the current carrying conductor that experiences a force when it is kept in the magnetic field. See here, the current carrying conductor, this is a current carrying conductor that experiences a force when it is kept in the magnetic field. So this is a magnetic field. When the electric conductor is placed, current carrying conductor is placed in the magnetic field, it experiences a force. So this is the working principle of electric motor. See here, this is a construction of electric motor. This is a magnetic field and this is a current carrying conductor. So the current carrying conductor is placed between of the magnetic field. Due to that magnetic field, it experiences a force. Due to that force, this coil started to rotate. That's why we are saying that the electric motor is convert the electrical energy into mechanical energy. When we give the electrical current, this coil is started to rotate. The rotation is the mechanical energy. Otherwise, we can say that the magnetic effect of electric current. The next one, construction. An electric motor consists of a rectangular coil ABCD of insulated copper wire. See, this is ABCD, the insulated copper wire. The coil is placed between the two poles of magnetic field. See, this is a north pole and this is a south pole. It is placed between the coil is placed between the magnetic field, such that the arm AB and CD are perpendicular to the direction of the magnetic field. What is the meaning of that? AB and CD are perpendicular to the direction of the magnetic field. See, you know that the magnetic field direction is always emerge from the north pole to south pole. So here this is a magnetic field direction. This is arm AB and this is arm CD. So the arm AB and the arm CD are perpendicular to the direction of the magnetic field. The next one, the end of the coils are connected to two cuffs B and Q of a split ring. Here PQ is a split ring. See here, the conductor is connected to the two halves P and Q. The P and Q are called split ring. So the end of the coils are connected to two halves P and Q. The inner side of these halves are insulated attached to an axle. See in this brown color. Here the P and Q are two halves. The inside of this is a P and this is a Q. The inside of these halves are insulated and this is attached to the axle. These halves are attached to the axle. See here. See, it was shown in this image. The external conducting edges of P and Q touch two conducting stationary brushes X and Y respectively. See, here P is connected to X and Q is connected to Y. That means this is half of B, P and Q. The P end is connected to the conducting stationary brushes X and Y. So here the X and Y are the brush. P and Q are the split ring. So this X and Y are connected to the battery and key. See here, it was shown in this image. Do you understand? The A, B, C, D is the rectangular coil. It is placed between the magnetic field and the end of the coil is connected to two halves P and Q. The inner side of the halves are insulated and it is attached to the axle, and the X and Y are the carbon brushes. It is attached to the P and Q. Now when we switch on the current, this is a positive terminal of the battery and this is a negative terminal. So the current direction is, this is the current direction. So current in the coil A, B, C, D enters from the source battery through conducting brushes X and Y, X, and flow backs to the battery through brush Y. So current enter into X and leave from the Y. Notice that the current in arm AB of the coil flow from A to B. So this is the direction of the current. So in AB arm, the current flow from A to B. In arm CD, it flows from C to D. So this is the direction of the current. That is opposite to the direction of the current through arm AB. So see here. In arm AB, the current direction is upward. The CD, the current direction is downward. So in the CD current is opposite to the arm AB current. On applying Fleming left hand rule, you know that Fleming left hand rule, the direction of force on the current carrying conductor in a magnetic field. So here we know the magnetic field direction and current direction. This is a current direction. So we know current direction and magnetic field direction. Then how we can identify the force on the current carrying conductor? Using Fleming left hand rule, we can find the force on the current carrying conductor. So you have to take your left hand and stretch your thumb finger, forefinger and middle finger mutually perpendicular to each other. The forefinger represent force on the conductor. The thumb finger represent the force on the conductor. The forefinger represent the magnetic field direction and the middle finger represent the current direction. So you have to take your left hand and see here north to south. So this is a magnetic field direction. So the forefinger represent magnetic field direction. In AB arm, the current is A to B. So this is a current direction. The middle finger. So the thumb finger shows the force direction. The same thing you have to use in CD arm also. This is a magnetic field direction. This is current direction. Here the thumb is in upward. So in arm AB, the force is downward. The arm CD, the force is upward. We find that the force acting on AB, arm AB pushes downward, while the force acting on arm CD pushes it upward. So here there are the two forces acting in opposite direction. When the two forces are acting in the opposite direction, the coil is started to rotate. So the coil and the axle O mounted free to turn about an axis. So rotate anticlockwise. So the force downward and the force upward. So this is started to rotate. The coil is started to rotate because it is freely mounted on the axle. At half rotation, see, after the half rotation, Q makes contact with the brush X and P with brush Y. See here, after half rotation, this is a D and this is C and this is B and this is A. After a half rotation, the Q contact with X and Y contact with P. But before rotation, you have to see that when the AB is here and CD is here, the P contact with X and Q contact with Y. After a half rotation, this is CD and this is AB. Q contact with X and Y contact with B. So therefore, the current in the coil get reversed and flows along the path DCBA. In starting, the current direction is A, B, C, D. After half rotation, the CD come here and AB goes there. So now the current direction is C, D, B, A. When the half rotation will take place? When the two forces are acting in the opposite direction, the coil is started to rotate. So a device that reverses the direction of flow of current through a circuit is called commutator. So the commutator is nothing but it is one of the device. This device reverses the direction of flow of current through a circuit is called commutator. Here which act as a commutator? This is a P and this is a Q. These two split ring are the P and Q. When the P and Q are rotate, it changes the direction of the current. That means in the starting the direction of the current is ABCD. After half rotation, the current direction is DCBA. So, which change the direction of the current in electric motor? The split ring, the P and Q, the split ring change the or reverse the direction of the current. So, in electric motor, the split ring act as a commutator. Normally, the commutator means the commutator is a device. It change the or reverse the direction of flow of current. Here the split ring act as a commutator. It is a very important point. In electric motor, what is the role of split ring? The split ring act as a commutator. The reversal of current also reverse the direction of force acting on the two arms AB and CD. See, after a half rotation, in CD arm the current is upward, AB arm the current is downward. Now you have to use the Fleming left hand rule. You have to use it. This is a magnetic field direction. This is a current direction. So this is a force. So in a CD arm the force is downward. For this side also you have to use the Fleming left hand rule. The current direction, this is a magnetic field direction and this is current direction. The force is upward. That means in AB arm the force is upward. Here the two forces are acting in opposite. Again this coil is started to rotate. Do you understand now what is meant by the electric motor? When we are giving the electrical energy, the coil is rotate. That means it is converted into mechanical energy. So see here, the reversal of current also reverse the direction of the force, because in a starting, in a CD arm experience a force upward, but now the CD arm experience a force downward. In starting, the AB arm experience a force downward, but when the current direction changed, the direction of the force is upward. The arm AB of the coil that was earlier pushed down is now pushed up, and the arm CD previously pushed up is now pushed down. Do you understand this sentence? Therefore, the coil and the axle rotate half a turn more in the same direction. Again is rotate. The reversing of the current is repeated at each half rotation, giving rise to continuous rotation of the coil and to the axle. So each and every half rotation, the current direction is changed. ABCD or CDBA. So each and every half rotation, the current direction is changed. Due to the current direction changed, the coil is started to continuous rotate. So see here this is north and south. So this represent north and south. For we are giving the current positive and negative. So we are giving the current positive to the coil and negative to the coil. When we are giving the current, here the motor is rotating. So due to the electrical energy, here the electrical energy is converted into mechanical energy. Do you understand how the working and the construction for electric motor? The electric motor consists of the two magnet, north and south poles. It has the north and south poles and the rectangular coil. When the rectangular coil is placed between the magnetic field, due to the current, it experiences a force. Due to the force, the coil is rotate. So how to enhance the power of commercial electric motor? So how I can enhance the power of electric motor? There are three ways. One is an electromagnet in place of permanent magnet. So instead of this permanent magnet, we can use the electromagnet. Large number of turns of the conducting wire in the current carrying coil. For in the center we are for this current carrying conductor consists of large number of turns. A soft iron on which the coil is wound. Using the soft iron, we can wound the coils. The soft iron core on which the coil wound plus the coils is called armature. This enhances the power of the motor. The armature is nothing but, you know that in electric motor, have you seen that the small iron core is, soft iron is present. In this iron we can see the large number of turns. This is called armature. See in this image. This is armature. Around the soft iron we can using soft iron core on which the coil is wound, that is called armature. So there are the three ways to enhance the power of commercial motor: using electromagnet in place of permanent magnet, and use the large number of turns in the coil. In a coil you have to use a large number of turns, and using soft iron core we can wound the coil. So this enhances the power of the motor. The next topic is electromagnetic induction. Any idea about electromagnetic induction? We have studied that when a current carrying conductor is placed in a magnetic field, see, this is a current carrying conductor. It is placed between the magnetic field such that the direction of a current is perpendicular to the magnetic field. You know that here the current direction and this is a magnetic field direction, and current and magnetic field directions are perpendicular to each other. It experiences a force. This force causes the conductor to move. So due to that magnetic field and current, we get the force. Due to that force, the coil is conductor or to move. That means the conductor is rotate. Now see these two images. Here this is a magnetic field and I am moving the coil into the magnetic field. This is a coil. I am just moving the coil into the magnetic field. See, in this case, I am not moving the coil. I am just kept the coil in between of the magnetic field. Instead of keeping the coil in between of the magnetic field, for here I am moving the coil into the magnetic field. And otherwise I am moving the magnet into the coil. So what would happen if I am moving the conductor into the magnetic field, or if moving the magnet into the coil, what would happen? Now let us imagine a situation in which a conductor is moving inside the magnetic field. This is conductor is moving in a magnetic field, or magnetic field is changing around a fixed conductor. What will happen? This is a small history about for the Michael Faraday. He is a Michael Faraday. This was first studied by English physicist Michael Faraday. So the electromagnetic induction is first studied by, that means the moving conductor in a magnetic field, or magnet is moving into the coil. This was first studied by the Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric current. See, by a moving magnet, we can generate the current. So this was discovered by the Michael Faraday. To observe this effect, let us perform the following activity. Michael Faraday was an experimental physicist. He had no formal education. He worked in book binding shop during his early years. He used to read books that came for binding. This way, Faraday developed his interest in science. He got an opportunity to listen some public lectures by Humphrey Davy of Royal Institute. So he is one of the English physicists, but he had no formal education. He is not completed their degrees. He worked in book binding shop and he used to read books. So came for binding. He made careful notes of Davy's lectures and sent them to Davy. Soon he was made an assistant in Davy's laboratory at the Royal Institute. Faraday made several path-breaking discoveries that include electromagnetic induction and the law of electrolysis. Several universities conferred on him the honorary degrees, but he turned down such honors. Faraday loved his science work more than the honor. Do you understand who is Michael Faraday, what he discovered, where he worked, what he did? He worked in assistance for Davy's laboratory in Royal Institute. He discovered the electromagnetic induction and the law of electrolysis. The many universities are conferred on him to giving the degrees, but Faraday not liked. Faraday loved his science work more than any honor. So what he done? What he discovered? He take a coil of wire AB. So this is a coil of wire AB having large number of turns. So he took the coil AB and he made this the wire into coil, the number of turns. Connect the end of the coil to a galvanometer. So this coil is connected to the galvanometer. In electricity lesson, we learned that voltmeter and ammeter. The voltmeter is used to measure the potential difference. The ammeter is used to measure the current in the circuit. What is the use of galvanometer? We will discuss. Take a strong bar magnet and move its north pole towards the end B of the coil. So A, B. He took the magnet have the north and south pole. The north pole of the magnet move towards the end B of the coil. Before going to see the activity, you have to know what is meant by the galvanometer. The galvanometer also have the two terminals. One is a positive terminal and another one is negative terminal. In ammeter and voltmeter, the zero start here and it has some values. In a voltmeter also the 0 is a start at the starting point. But in a galvanometer the 0 is the center, the other values are present left and right. When the galvanometer used to detect the current can detect the presence of current in a circuit. That means if you take any wire, the wire is directly connected to the galvanometer. Here there is no battery, so there is no current. When I connected the conductor to the galvanometer, it shows 0. That means there is no current in this circuit. If maybe is there any current produced in this conductor, the galvanometer deflect right or left. So the galvanometer is used to detect the presence of a current in a circuit. It is not used to measure the current of the circuit. It is just to detect the presence of a current. The pointer remains at 0 for 0 current flowing through it. When there is no current in the circuit, the galvanometer shows 0 reading. It can deflect either to the left or to the right of the 0 mark depending on the direction of the current. If maybe the conductor have the current, this needle can deflect right or left according to the current direction. So here I connected the galvanometer to this coil. When I move, see this animation. When the north pole of the magnet is moved into the coil, the galvanometer shows some deflection. So from this what you understand? Here I am not connected any battery. If battery is connected means there is current flow. Here there is no battery. But when I am moving the magnet into the coil, the galvanometer get a deflect. That means in this coil some current is produced. So this type of current is called induced current. The current is induced. So do you find any change in the galvanometer needle? Yes. When I move the magnet towards the coil, the galvanometer shows some deflection. There is a momentary deflection in the needle of the galvanometer says to the right. Maybe it move right or left. This indicates the presence of a current in the coil AB. So when the galvanometer shows the deflection, this shows that in this coil the current is present. The deflection becomes 0 the moment of the motion of the magnet stop. See here. When the magnet is moving, the north pole of the magnet is near to the B, it shows to right. See the magnetic needle direction. When there is no motion, just I kept the magnet into the coil, the galvanometer shows 0. That means there is no current in the coil. When I move out the magnet, the galvanometer shows the deflection in the left side. So north inside means right. If there is no movement means there is no deflection. When we take out, the galvanometer shows left side deflection. So place the magnet stationary at point near to the coil, keeping its north pole towards the end B of the coil. We see that the galvanometer needle deflects towards the right. When the coil is moved away towards the north pole of the magnet. Similarly, the needle moves towards the left when the coil is moved. So see this animation. When the magnet is in, the coil shows direction here. When I take out, the coil shows the left side. See here, the coil is moving inside of the magnetic field. But here the magnet is moving inside of the coil. So when the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to 0. If there is no movement in the magnet, means the galvanometer shows 0 deflection. So what do you conclude from this activity? And you can also check that if you have had moved south pole of the magnet towards the end. In a starting experiment, we moved north pole towards the B. If you moved the south pole, so what would happen? When we move the north pole, the galvanometer shows the deflection first right. When we take out the north pole, the galvanometer shows left. When we move the north means left. South means in a first it shows the left. When we take out, it shows right. That is opposite to for north pole. So the conclusion of this activity says that it is clear from this activity that the motion of a magnet with respect to the coil produce an induced potential difference which set up an induced electric current in the circuit. So how we can generate the electric current? By moving a magnet into the coil, we can introduce the electric current. So this was discovered by Michael Faraday. This is a homework question for you. What is the principle of electric motor? What is the role of split ring in an electric motor? A coil is insulated copper wire which is connected to galvanometer. What will happen if a bar magnet is pushed into the coil, withdrawn from the inside the coil, held the stationary inside the coil? Draw a labeled diagram of an electric motor. Take your science book and open the chapter number 13, Magnetic Effect of Electric Current. See the topic 13.4, Electric Motor. So this is a definition of electric motor. An electric motor is a rotating device that converts electrical energy to mechanical energy. And it is used in electric fan, refrigerator, mixers, washing machines, computers and MP3 players. And this is a construction for electric motor. It has magnetic field and the coil is placed between the magnetic field. The coil is connected to two halves P and Q, and the halves are connected to the carbon brushes X and Y, and it is connected to the battery. Using Fleming left hand rule, we can find the direction of the force on the conductor. And this is how to enhance the commercial motors. Use an electromagnet in place of permanent magnet in a large number of turns using a soft iron core on which the coil is wound. The next topic is a 13.5, electromagnetic induction, and it was discovered by the Faraday, English physicist. And this activity I explained that means you have to take a coil, and the coil is connected to the galvanometer, and you have to move the magnet into the coil. Due to the movement of the magnetic field magnet, the current is induced in the coil. That current is called induced current. So I explained about that what is meant by the galvanometer. The galvanometer is a device. It is used to can detect the presence of current in a circuit. So the next class we will see the activity 13.9. Thank you for watching. If you have any doubt in this topic, you can ask through Teachment.